All right, we're going to talk about projectiles a bit. So, wanted to sort of kind of delve further into how you could use, say, GeoGebra to explore something, a little bit of algebra going on, a little bit of GeoGebra, solving something that could be actually kind of difficult, I think. We'll see. I haven't actually done it yet. We'll see how this goes. So, the idea is, we have this thing, we've got um, some kind of projectile thing going, let's say this is at 6 feet of, of the ground, and it shoots out, say, like Nerf gun or something, or a gun, or whatever. It's got a it's got a direction here, and we'll say that it always comes out at, say, I don't know, 10 feet per second. So it's kind of like 10 feet per second. Now I'm going to use v here, kind of standing for velocity. Velocity is both direction and magnitude. So it's the 10 feet per second, but also the direction it's going in. So that's velocity. Speed is just the 10 feet per second. So I should use s, but my s's often look like 5s. So I'm going to stick with v. That's all right. And now the idea of this 10 feet per second is that it's, immediately after leaving this thing, if you were to measure it just like here, and then just a little bit farther on its trajectory, and figure out the change in the distance or the change in time, that would be the speed, okay? So that's literally what it is. Over time, that speed is going to change because gravity is pulling it down. In reality, we also would have some kind of like probably air friction or something, but we're going to ignore that. So it's just gravity that's going to be changing it. Gravity's pulling the thing down, so it's just acting on sort of pulling it downwards. It's accelerating it downwards, and so over time, it'll kind of um, um, so yeah, it's basically going to be what it looks like in terms of this velocity. The direction is going more and more down, and it should actually be accelerating, although probably less so in the vertical part. All right, so that's kind of roughly what we're thinking about here. And so we're just going to start with that h of t, so that's the height, is we have this gravitational constant, minus 16t squared. So that's given by the mass of the Earth, basically, plus the velocity in the y direction, so v sub y, as we say. It's nice to have names like that. They tell you something about what you're doing. And then plus 6, because that's the starting point, right? So that's just it going up and down. We need to figure out what Vy is. And then there's also the distance in terms of the x. I call it, this is x distance. And so this is just simply the velocity in the x direction times t. That doesn't change the whole time. It's just going always the same thing. So at this at the top here, when the angle has become horizontal, that actually will be, at that point, that's just going to be Vx, the original velocity. The Vy has gone to 0, and then it starts going negative. Right, so that's when it starts coming down. Okay, good. All right, so this is kind of the two basic equations involving what time is doing for us. We don't know what Vx and Vy are. Now, Vx and Vy, well, if this is V, then the direction here, that component will be Vy, and this one is going to be Vx. Why? Well, basically, think of actually that little bit of distance here along the tip here. So like if this was after 1 second and we ignore gravity for a moment, then you'd have the point here and would have traveled, let's say it's t equals 1. Then the x location is going to be the speed of the exchange. It's just 1 times that. That gave me an x location, and that's what this vertex is. This is actually going to be Vx, Vy at that point. And if it was an earlier point in time, it would just be a scaled version of that appropriately. And same thing with the Vy there. That's what you get. So that's why that triangle is coming about. Given V and this angle, there are functions that will tell you what Vx and Vy are, namely sine and cosine. These are trigonometric functions. We're not going to do that right now. Instead, we're just going to use GeoGebra in a circle to kind of control this picture. But now, what might we want to care about? We might care about where's the maximum located, right? How far does this thing go? As I change the angle, keeping the speed the same, how does that affect where the final place lands? Is there, what's the maximum distance it can go? What's the minimum? The minimum's easy, just straight up, right? So, yeah. So that's easy. But, is having it shoot out sort of like this, is that going to get you the farthest? Or should it be a little angle so you get a little bit of lift before the gravity smashes you down into the ground, right? These are questions. So how do we answer them? Well, we could graph functions involving t, involving x and y. That's slightly complicated. So instead, what we're going to do is we want to convert this to an x and y kind of picture, right? So right now we have vxt, and then we have all of this here. And so if this is supposed to be our x, then t is equal to x over vx. And so we can replace t and the other thing with that x. And so if we have x, then we can just do minus 16 x over vx squared plus vy x over vx plus 6. So that's going to be our basic graphing equation. Now at this point, I'm just going to go over to GeoGebra. All right, so first of all, what did I say? 10 feet per second. So I'm going to do a circle, center and radius here. I'm going to have a radius of 10. To change that, but all right. And now, basically, I'm going to put a point on this thing. There we go. As I drag the point, right? Now that's representing my overall velocity. The speed is 10, and the direction is right here. And so, what do I want from this? So if I do this, give myself xb0, and then 0yb. So I plotted on the xy coordinates basically where vx and vy are. And if you want to, you can get a little viewpoint of segments here and here. And so as I drag this along, so the height here gives almost the entire speed until it is there. And then as we come down, we get the horizontal speed to be almost everything, right? So that's just how this thing works. I'm going to get rid of these segments now, and there we go. And now I'm going to try to, so given Vx, so I'm just going to call this, so take this Vx equals, so what was Vx? That's that length, so it's the distance between A and C, right? Vertical, horizontal distance. Yeah. So that's like 8.2 here, and then By is equal to the distance of A and D. Alrighty. And as I move along, you can see how it goes, right? Good. And now I'm going to graph a function. So minus 16, and this was x divided by Vx squared plus Vy divided by Vx times x plus 6. So that's my parabola. And now I can get the extremum there, and I can get the roots. And I'm going to want to, this setting, give it to a value. There we go. And do this one. Okay. So we've set up our parabola, and now as we change the angle here, you can see what happens. And it goes almost, so as it gets very vertical, it goes very little, even though, it goes to the highest point here. That's the highest it can go. It's basically 7.56 before it gets brought back to Earth. And then as we go higher and higher here, look what happened. So if it was purely vertical, horizontal, it would go about 6.12 from a starting point 6. I guess that'd be feet. That's that. But as we increase the vertical a little, vertical speed, it goes up, right? It keeps on going. Looks like 6.87 is about the max. So it's not a big difference in terms of the overall, I guess, but it definitely is a difference. And if you wanted to know the angle, we've got an angle function here. Angle, there we go. That's an angle of 26.51 degrees. That looks like that's the maximum for this setup to go. There we go. Now, that is of course with the, so what affects that? Well, we've got a few things here. Let's say we were to start at 12. Would that change anything? Well, it changes certainly how far we end up going. Does it change? Does that change where the maximum is located? Looks like it. Looks like it's now like around 16, 17 degrees. So the more, so it's this trade-off, right? The higher you are shooting, the farther you can go with that. So the less you want to spend on the up, I suppose. You want to get as far as you can. And if you were to go in the opposite direction, with the 1, where would that go? So what's the, that's a little scrunched here. Those things out of the way. 3.5, 3.7, 4. So that's a very little distance between the ground and the thing. The max is around 4, compared with shooting it vertically, which leads to like 2.5, right? And horizontal. And so vertical, good. What else can we change? We can change, well, we could change the radius of the circle. So here, this point is 26.57 degrees. Is that affected by the radius of the circle? Well, let's do 20. Okay, so obviously you can go farther, but the maximum angle here, what was it? Yeah, so that changes it too, I guess. Again, the faster the speed before it pulls in, so there's this gravitational thing. So, yeah, speed matters. The height matters. And obviously, if I were to change the gravitational thing here, okay, well, let me go back to our original circle. There we go. And what happens if I lower the strength of gravity? Let's say it's half as strong. What happens with that? Well, so I think, what was it, 26 degrees or something was around here. 10.6, that's going down. Is it going up? No. So that doesn't seem to care. What about very strong gravity? So again, 4.72, 4.77. So it does. So that got stronger. Well, what about the, if you do a 0 here, of course, it's no longer a parabola. and so it never hits the ground. So here, very weak gravity, you can go much farther. You can kind of see it's going farther and farther and farther and farther. 36.50, there we go. Somewhere around here, 56.7, 42 degrees. So, okay, all these different parameters can lead to different effects. And so this was just a way of sort of playing around with these parabolas. You could, of course, actually kind of, given the velocities x and y now, so you could write down the velocity y in terms of velocity x and the v, because it's the Pythagorean theorem, and the x you can get from the theta, and so you can just, with constant speed, but during theta, using those trig functions I mentioned, you can, get to what angle that should be formulaically. You put that in there, and you look at whatever you want to vary and play around with it. It's going to be a little messy, but as one kind of flounders with these things, I think it's useful to always keep in mind. You can put it in GeoGebra and try to model it. You don't have to solve it blindly, right? You can say, okay, it's supposed to be like this or this or this, and whatever. As I said, one could go into more depths analytically with this stuff, but I think that's just going to get messy. I hope that just demonstrated some of the potential of GeoGebra.